I think we can begin. Okay, so let me first introduce myself. So I'm Atte Rekorpi. I'm a data scientist at Datrix. As my educational background, I have a master's degree in computational physics from the University of Eastern Finland, and currently I'm a third-year PhD student at Politecnico di Milano, doing a PhD at the Department of Physics in another Marie Curie-funded doctoral network called Concise, but more about that in the afternoon. Because today the goal of this lecture is for you to learn about learn about the multi-layer perceptron, which is one of the core neural networks still being widely used in many applications, and for example, large part of GPT. The goal is also for you to understand how the different layers, weights, and activations work together to make predictions, and actually gain a good understanding and grasp on how the MLPs learn through backpropagation and parameter updates. And how many of you have taken courses in calculus or have like a grasp of the? Okay, good. Well, what about multivariate calculus? Okay, linear algebra. Okay, there won't be any linear algebra here, but calculus will be useful. But even that I try to keep down low. And of course, I want you to be able to recognize when MLPs are strong and where they fail and why they still remain relevant today. So, what are neural networks? Well, I would strictly categorize them as under the deep learning umbrella. But before we go into the MLP stuff and actual stuff, let's give a little recap on yesterday what Elia told us. So, basic linear regression models learn single linear mapping or boundary decision or some simple linear. And there are also logistic regression models which can also do the same stuff. But the limitation of these simpler models and thoughts is that many of the real-world applications and problems are non-linear, not only non-linear, but also the composition of like vision and speech. It's not a very easy problem to solve. The stuff we did yesterday with just a single regression model. So, main idea of a neural network is to combine many simple units. Let's start with linear units because it's easier. And hopefully this will help on linear structures and compositional problems. So as yesterday, simple problem XOR is not solvable with a single linear model, but you need multiple dependencies. Okay, so that was the recap of yesterday, I guess, in some sense. Okay, so let's go into the perceptron and neurons and MLPs. So historically, these two guys, I read their paper like 5 days ago. They kind of drew inspiration from biological neurons, not really. But they did have illustrations of neurons and the computational neurons, but they didn't actually draw any other inspiration other than that both neurons take some input, do something to the number, and give some output. So I think the key takeaway you should take from this slide is that as our Huber says, you never actually use this comparison seriously, at least, because first of all, neurons only fire photons, and they are much more complicated, while the artificial neuron you can think of just as a number which has some operation done to it, and it gives some output, and it always gives some output, unlike neuron, real neuron. Okay, so as you probably know, neural networks are collections of interconnected neurons. I guess some would call it a single neuron perceptronic. It's a binary classifier, but all neurons are perceptrons. And together they represent the function, compositional function. Each neuron has a weight or weights at this one, as well as inputs, which from now on are x vector. And the neural network learn by adjusting the weights. But more about that later. This can map nonlinear and hierarchical mappings by stacking layers, and each layer transforms data. So you have some input, you do something to it, you get some output, and you can stack this together. And now it's the key point here. All neural networks are differentiable. And this is a key, which I will explain later, but you should remember this. Okay. Neural networks, of course, are not hand programs. They learn from data automatically. So, unlike these things here, programmed things, it's not the answer. Number 4, basically they are edge detectors. So when you compare hand explicit feature selection or hand programming these, I don't know. Okay, so if you want to hand program a program which is able to detect numbers, like the MNIST dataset, it's a very challenging program to do it. Actually, I don't think anyone has done it, because sure you can get edge detectors, this kind of stuff, but then how do you generalize? So the idea neural networks is to just hope, basically, that the networks learn something. So in MLP, you vectorize everything, have the inputs, and then you have layers that do something to the original input, and hopefully you get the correct output. You would wish that, for example, the first layer learns these edge detection patterns, and the second layer learns something more useful. But actually, that's not how they work really. And of course, this is a pretty wild assumption to make that okay, the model will just learn stuff. But as you can see later, it's actually pretty simple process for the model to learn this stuff. Okay, so let's actually go through the neuron step by step. So we have the inputs X, we have the weights, so you multiply each input by its corresponding weight, and you get some output. You also can have biases, so after you have multiplied all the input, you add some weight to them, and you get the Z value. Now, after that, usually you have some kind of activation function, which can be linear or non-linear, but usually non-linear, and then you get the output from that. So that's the simplest block we are working with, single neuron. Of course, when you stack these together, you get layers. Yes, you stack them next to each other. And then if you stack layers after each other, you get multi-layer neural network. And I think the common opinion is that you get it's not a deep neural network until you have a couple layers. Okay, so let's look at how the inputs pass through the layers. So actually, let's do it step by step with this tiny MLP example. So we have inputs 1, so 1 goes here, 2 goes here. Then we have the first layer has these weights, so because we have 4 arrows, we have 4 weights and 2 biases. So weight 1. And let's define the weight, the second layer as well already here. So weight is there, and it has only 1 bias because we have only 1 output. And for the activation, we'll just use rectified flare unit, which is a max of 0 around the input. I'll explain why we use it later, but let's just go on with this now. Okay, so let's compute the forward cost for the layer 1, so with weights 1. So first of all, we calculate this one. So we take the input 1 times 1, and then this here. I'll use the other mouse actually. It's here. Yes, this is. Okay, so input 1 times the first weight, and input 2 times the second weight, which gives us you also need to bias, so you get minus 0.5. Then you put the same for the second row. So 2 times 1 plus 0 times 2, and take out the bias, you get 1. Okay, well, super simple. Just all the activations work like this. Anyway, let's do it. Now we need to apply the activation function for each of the nodes. So we are using rel. So 0.1 is just 0, and max of 0 or 1 is 1. So we get 0 and 1. Okay, and then the second layer. It's super simple. Just do the same stuff again. We get the dot product, add bias. So we get 2.1 and this is, yeah. And that's basically it. MLPs are super simple in the forward way. You can see. So let's talk about the activation a little bit, because not just randomly triggering the relu, but why do we actually use relu or other functions as the activation function? So if you think about it, if we use a linear activation function and stack many layers and a complex network, it's still a composition of linear maps, which means that the whole network is still linear. So giving the nodes activation functions which are nonlinear gives the network much more expressive power. And here are the common activation functions we have used. Sigmoid and Manage historically used, not so much anymore. Relu is much more modern because it mitigates this thing called vanishing gradients, which we'll come back to later. Okay, so also this is an interesting point. Basically, a network with at least one hidden layer and nonlinear functions, activation functions, can approximate any function to any precision you want, even you have enough units in the layer. But practically, this is not how you build your networks, because that is actually pretty useful. We can discuss this if it's interesting, but for now I'll skip the explanation why this is the case. And also would train this trumps all this anyway. Okay, so now we know how the network goes forward, but we have no idea how we actually make it learn. So here comes the first functions, which I by designing models is actually the most important part, usually. So the multi-layer perceptron defines a mapping from the inputs to some output, and is parameterized by the weights for it. So the loss function tells us how wrong the predictions of the output of the model is, and how wrong it is called the loss. So this is super simple, but let's just go over it anyway. If the true answer is 1 and the model predicts 0.7, it's a small loss. Whereas if it predicts 0.1, it has a large loss. Okay, and you again remind here that the MLP and every neural network is differentiable in relative to its parameters. So here's the official, I guess, definition for a loss. So loss is a function, the parameters, technically. But it's calculated as the average of all the training samples. The goal when we teach the model is to minimize the loss, of course. And you basically reduces to minimizing the loss over all the parameters. Okay, so we have a couple examples of different losses here. So mean square error is useful when your outputs are not categorical, but real values range. And classification uses cross entropy usually, and these are the most typical cases for loss functions that are used. But of course, we have many different loss functions we use, like losses and transcurrents and so on, depending on what we are doing. Okay, I think we can probably skip this part. You can think about the loss function from a statistical perspective, probabilistic modeling perspective as well, but this is relevant here. Okay, so summary recap of where we are. So neural networks define a parametric function. It takes an input, and depending on the parameters, gives some kind of output. And the loss function tells us how wrong or right the predictions are to the desired outcome. And training is basically just adjusting the parameters to minimize the loss. And now we come to the actual lecture topic, I guess, backpropagation. So this is the way we actually compute gradients and the gradients of the parameters, which tells us how much they need to be adjusted. Okay, so we have some input, number 4 here. Our model gives us 98% probability that it's a 4 and 2% probability that it's a 9. We want to make the model better. How do we do that? We need to adjust the weights on this layer so that these weights here are higher than the ones that got answered here. Okay, well, that's simple to do, but actually these weights depend on the input, or also depend on the output of this layer, which depend on these layers. So sure, we could manually calculate how much we need to change these and then how much that affects these and so on. But that's not very computationally efficient. So we actually have a tool for this, which is backpropagation, which uses a chain rule on the computational graph. So here's a refresher if you don't remember how the chain rule works. We have a function y, which is a function of another function, which is a function of x. So the derivative of the function relative to x is just the multiplicative of the function, the other function. And in the case, which is what we are using here, the partial derivative is just this. So hopefully this is clear. Okay. So this is also a key point. So any neural network can be represented as a directed acyclic graph of elementary operations. And this just means that if you know what DHGs are, they are graphs which don't loop on themselves, so they are directed and you never come back further. Okay, so of course each node goes the forward polygon or the activation of the neuron, and we at the same time we save the local derivative and how its output changes with respect to the inputs it's getting. And backpropagation is basically just reversing graph backward and applying the local derivatives to get the global gradients of the network. Okay, there's a typo here. Usually it's divided by 2. Okay. So actually, let's do this for a little network. But not for not together. So set up this like this. Forward pass is what we previously, but we also calculate the loss. So check the time. Yeah, okay, so first we start from the loss, and we want to calculate the partial derivatives of all the nodes in the network. Well, you just follow the chain rule. So confusing to have so many screens. Okay, so you have the loss, partial derivative of loss in relation to the layer 2 weights. And if you just follow the chain rule, you get this. And of course, in the layer 2, you also have biases, so you need to take those account. And you get this. And then you just take these and propagate them backwards. This becomes quickly a very big multiplication task, but it's not complicated. You just unfold the partial derivatives there. So I think this slide should be here. Well, let's go through it. So one key point is that all the partial derivatives depend on the local quantities, which were already computed when we went forward in the network. The backwards pass is just the mirror of that, and we have all the values we basically needed, just with the loss values. Slide was not supposed to be here. Sorry. Okay. Let's do this is a really tiny network we are going to work through now to calculate the gradients. So we have the y here, which is our output, and we want to calculate the gradients of the loss related to the parameters w and v. And we want to compare it how the loss behaves versus like a numerical calculation of the loss. So let's just give some random values to the page. It's stuck. Okay. Okay, so goal is to compare the backpropagation calculation to a numerical approximation for this really tiny network, which is you can't even contact that. Let's do it anyway. So let's give a random values, for example, these to the weights at the bias, and let the input be like 1 and the real value of y is 0.5, let's say. So the forward pass, I think we need to go for this. Get the output of from value of x. The network gives us output of 1.08. So the loss, if we define it like this, becomes 0.16. Also using real values. So also we are calculating the partial derivative in relation to this, not this. So we need to go all the way back. So we have the here, and all the components are here, and yes, we have that. So you can see that the okay, I'll teach you about RELU now then, because I didn't tell you about this. So RELU is an interesting function because it's an identity function when the input is more than 0, and it's 0 when it's less than 0, which means that the derivative of it is always 1. Which makes a calculation super easy because it's always 1. So we have the actual prediction by model minus the real value times the weight here. And these are calculated here. So you can see that the H of the is 1.2, and it's just when the L is at the positive A, you of course get 1. So we get this value here. And this is this part here. Now we want to compare this with the numerical approximation. So I just put the epsilon of 10 to the power minus 5 in the calculator here, and we get this value here. And this is basically exactly the same value, at least in unless you got this here, as the analytic solution via backpropagation. So we can conclude from this one example that the backpropagation is very efficient differentiation first in the network, and it's not an approximation heuristic. Okay, this is the correct slide. Okay, so again, the backpropagation is just chain rule on the computation graph backwards. And we have the forward pass, which computes the outputs and stores the intermediate values, and then backward pass, which calculates the gradients using the local derivatives. and it's very efficient. And it's basically every deep learning method uses the backpropagation method. It's also called automatic differentiation systems. And next up is gradient descent, but do you want to pause here or directly? Okay, good. Okay, so now we know how to calculate the gradient or the partial derivative of the loss in relation to the parameters. So gradient descent is just how we update the parameters. Of course, gradient tells us the direction of the highest growth of the function. So if we have a 2D case, it's simple to visualize. But of course, we have in a real network, we have millions of directions because we have millions of parameters. So it's not so easy to visualize. But in 2D, it's visualized. And if you think about it in 2D case, gradient tells us the highest direction of the function. And we, of course, don't want to go up, we want to go down. So we take the negative of the grades and update the parameters in that direction. And of course, we need to also decide how much we go downhill. And this is where learning rate comes in. So, as I just said, you can interpret this as gradient is the negative gradient, I should say. It's the direction of the steepest. No, it's correct. I read it wrong. Gradient is the direction of the steepest increase of the loss. Negative gradient is the steepest decrease in the loss. So you can think about it as it's stuck again.
Just a bit of connection. It's
Okay. Yeah, so you can think about the gradient descent as falling in a hole. Okay, then let's. This is where I think linear algebra would be useful, but I have not included it here because I didn't think that there would be enough people who could follow it. But if you want to learn about linear algebra perspective, there are many tools online. I think it gives the best overview of how the learning actually works. But yeah. So how data works? So we have the empirical risk and the gradient for it, and we need to think about how each sample actually contributes its own gradient. And full touch of the data we have is the average of all those gradients, because each sample, of course, has its own gradient and minimum of what's the model to be. So, for example, if we have a MNIST model and we just give it one value of 4, then all the weights will, of course, go downhill in the direction that predicts 4. But when we give more samples, different properties, the average of those hopefully makes it more general. So usually we actually don't work with the full batch because we don't have the computational capability as memory to handle all the stuff. But if we did technically, the gradient descent would find the most straightforward path to that minimum. But usually, sure, the other option is to just give it one sample at a time. It's noisy, but it gets there, as you can see. But actually, what usually is done is using mini batches. Gradient descent, it's the optimum between these two. You want to make your batches as large as you can, but well, I guess it depends, because the interesting thing is that having mini batches, not the full batch, makes the process noisy, and while the whole batch can get stuck in a local minima, using mini batches introduces noise, which may help you get out of the local minima and jump into the better, probably not global, but better minimum. Okay, so that's just it. And yes, a quick linear algebra perspective for you. So each gradient is basically a vector in the parameter space. And the average of all those is the mean direction of the data. And gradient descent is like moving along the projection of the data errors on the different parameter directions. Okay, so let's talk about learning rate and step sizes. So learning rate is what controls step size. If we have a too small step size, the convergence is low, and this of course is computationally costly. So it takes too long to find the minimum. If it's too large, the model can diverge or have these oscillations and settle down in the minimum. Then, of course, instead of having just some set learning rate or step size, you want to usually use some kind of adaptive method which will adjust the learning rate. Also, there's this point that the more noise we need usually, the more noisier the data you have, you need the slower learning rate. Okay, so here are some variants of the gradient descent. There are, of course, many. Here's the most common ones. So we have the momentum, remembers fast gradients, damps oscillations, and accelerates consistent directions. So we have this velocity which is dependent on the previous velocity, the previous gradient of the loss. This gives us the new, along with the learning rate, the new parameters. And this is usually used alongside with scaling, which gives us the most commonly used learning rate scheduler, I guess, called ADAM. I think this is currently the most used variant of the gradient descent machine learning. Of course, like ADAM W and so on, which I use, but this is the default one, I think. Oh, I didn't explain scaling. Yeah, so RAM has a momentum, but it also has scaling, which just adjusts the step size based on the magnitude of the gradient. So if the gradient is steep or not, decides on how large a step to take. And in a big picture perspective, this is just a refinements on stability and speed. These are not like technically necessary for the model to learn anything. Okay, yeah, here's a summary of the gradient. So it's a iterative optimization of the parameters in the network using a gradient information from the data of the batch. There are different variations like Adam, channel noise, and curvature and scale differences. Again, learning is just optimizing the network, and learning in machine learning is, or I should say deep learning, is this process of gradient-based parameter updates. And again, from linear algebra perspective, gradient is just the sum of the Jacobian residual products in a vector form. Okay, next up, initialization. How to initialize the weights and why it matters for gradient flow. Okay, let's start again.
It's unstable for the
Switch.
Yes.
Okay, so let's say we initialize all the weights to 0, which just means that all numbers are identical, and basically this means that the networks get stuck. It's symmetrical, nothing can handle different gradients. Then there's also this problem. If the weights get too small or too large, activations can blow up or vanish. So remember the multiplicative effect to really hit this. So because all the weights get too large and you multiply the mix. First, the last layer might be fine, but as you back propagate, they vanish, go like 0, and learning becomes super slow. And same with if they are too large, sure, the first layer might be fine, but then you run out of memory because the weights get too large. So the key idea in initialization and making the weights behave properly is to preserve the variance of activations and make the gradients behave. Typical strategies are like Sagerano-Lorentz initialization or finding wherever. And there are others, but these are just some examples. Okay, now we get to the real stuff. So previously, I don't know how many years it has been, but originally that is used as an activation function, sigmoid or hypertangent. These are nice nonlinear functions which are smooth and they were biologically inspired originally, but the problem they have is that they saturate, they get small, the gradients get too small, and this slows down the learning process. So instead we use ReLU. The gradient, the gradient is always, derivative is always 1, unlike with hypertangent and sigmoid. The slope can go too far, it gets too close to 0. This always stays either 1 or 0, which actually causes its own problems in fact that resolution gets stuck at 0, but let's fix for that as well. And also, ReLU is just very efficient in computation because it's so simple function. Surprisingly, it still works very well. There's also different variants of ReLU being used, like leaky ReLU or ReLU or ReLU. These have different measures in smoothness and stability and computational costs, which personally I like the leaky ReLU, which is not shown here. It's unlike these two, it's also not continuously differentiable at 0. It's like a ReLU when it's larger than 0, but it has a small slope as well, so it can get stuck, but it still remains computationally very cheap. So interesting question is why can we use ReLU when it's not continuously differentiable at 0, even though just as we have seen, networks need to be differentiable to be able to do the back propagation. So the reason is that it's kind of funny. So it really doesn't matter that one point is not continuously differentiable because it's highly unlikely that you get exactly 0 value in training. And even if you get, you can just say that okay, this value is something else than it's supposed to be. So you can manually define B if that's the case. And even if that seems a little strange, it's fine because it's so rare that even if you miscalculate one point and arbitrarily decide it to be different, it doesn't matter because it doesn't happen. It doesn't happen. So in grand scheme of things, it's not. It doesn't affect the learning process at all. Okay. Then a little bit more about the vanishing and exploding gradients. So again, with the sigmoid and hypertangent, if the derivative is less than 1, the product of those back propagation shrink exponential and the gradient vanish and slow down the process, and then the derivative is larger than the explode and too large. So I guess this is a recap. So there are some solutions besides ReLU. We have the initialization ReLU, and then we also have gradient. This basically just means that we don't allow larger gradients than we decide. So even though the calculation gives us this large gradient, we just say that okay, you are limited here, and then it cannot explode. Or if we are worrying about vanishing gradients, we just say that okay, gradient cannot be lower than this, and then the multiplicative effect won't. Of course, this has this of course can slow down. Other thing we can do is normalize the layers. So we have these ones here, activations before, and then we can just center them on 0 again and get normalized activations, and this helps stability the networks. Here are some examples of different normalization strategies we are using, like a patch norm, air norm. These help with help smooth the learning process and converge faster. Okay, then we also, of course, have regularization. So we can use weight decays and dropouts and early stopping. So here you can see the learning process. The model learns well until this point, and it continues to learn from the dataset, but on the actual problem, it did here, and after that, it doesn't. So basically, after this point, it no longer generalizes well. It only learns about the training dataset being used. So we probably want to stop the training here, and here comes the early stopping. So you can make different educated guesses on when you should stop the learning and detail as a task. Then weight decay is different thing. Basically, if it basically, how would I explain this? The trained weights are allowed to decay, meaning if they are not updated often enough, they will change their values randomly to make model behave differently and get more noisy and generalize better. Okay, and then the final part is the element dropout, which basically just means that we give some percentage of chance for the neuron to not activate during the forward and backward. So it gets completely ignored, which I guess the theory is that it makes the model more robust and not reliant on single neurons to do something, what's important. Instead, it's more collaborative. So I guess in summary, I would say that actually what you usually do when you train a network is not really about just the gradients. It's about keeping the signals and gradients directly stable. If you can do that, the rest follows. Okay, yes, I guess this is like a recap of how the learning process works. So neural networks are parametric and differentiable functions trained via gradient-based optimization, and they try to approximate arbitrary things from the data they activate. The three central ideas are that they are representation learning programs. For the layers you get more features. This would be another lecture topic about how this actually works. As I mentioned earlier, it usually matters more neurons you have in one layer. Again, they are differentiable because they need to be in order for them to be optimized with the backpropagation. And they're kind of statistical if you don't use the full batch sequence, which you will use. And the full pipeline is just so you have input, you calculate via the network some output, you calculate the loss from the output, you backpropagate that loss, you calculate the gradients, then you use some kind of gradient descent method to update the parameters, and you do that loop until you have a trained model which is able to make predictions. Okay, that was the main topic. There's other stuff, but I guess we can just jump into this. This is not won't take too long. Okay, so that was just about the multi-layer perceptron, which is basically the simplest network you can think of. Just has simple neurons that like layers. Then, of course, there are many different more modern architectures like convolutional neural networks, which are good for image recognition and spatially structured data, 3D tomography, and so on. Then you have recurrent neural networks or gated recurrent units or neural networks or transformers, which are the new hot topic, the LLMs and so on. These are good for temporal and sequential data types, like text and speech and so on, video and so on. And then you, of course, have a graph neural networks for relational data. I'm not too familiar with these networks. So, the multi-layer perceptron, the typical neural network, you think about is built of these neurons. But for example, this is the transformer, and this is what is used for different transformer models. So, as you can see, it's quite a bit more complicated than a simple neuron. But the basic idea is still the same. You have some inputs, you get some outputs, and you build a network around this. Of course, it's not that simple because you also have outputs as the inputs, but the backpropagation still holds. And then, for example, this is convolutional neural networks instead use convolution operations instead of simple addition multiplication. So you can have a one-dimensional CNN or 2D CNN with 2D convolutions or 3D convolutions, and so on. But usually you don't go too much higher because the convolution operation in higher dimensions is not computationally very cheap to run. Okay, I just want to say that the big that saying that neural networks are like some kind of black boxes is that useful because technically we know exactly what's going inside them. It's just that they are so complicated that it's not easy to analyze them, but it's technically possible. So should always be that caveat. Also, all the future and current, well, I should not all the future, but the current, well, definitely all the current models are just refinement of the extensions of the concepts we went over here. So backpropagation is still, or way the models learn today. So even like GPT-3 still uses the multi-layer perceptron as the major part of the network. So you can see that actually 65% of the parameters in GPT-3 are still just some random place in the multi-layer perceptron. Of course, this simplified pipeline of the GPT-3 is notice that there's 96 blocks of these here. So you have a normalization, you have the attention transformer, another normalization layer, then you have the MLP, and then you stack these blocks 96 times together and you get the ChatGPT. Okay, I think this is an important point for the exercise to look at to understand these two operations. So this is a 2D convolution. At the right, we are going to use max pooling. So max pooling is just taking the max value from a sector, pulling it down. You also can use average pooling, but max pooling is usually being used. How many actually like understand how the 2D convolution works? I should have a slide of these. I don't have a slide to these how 2D convolution works.
You can draw. There's a board.
Yeah, I think it's actually easier to just look at the animation. So we have a like a filter which has the numbers. It's fast. Yeah, I have yes, it's small. I can teach it in the exercise session. Let's just go through the presentation. Okay. So UNet, probably many of you know, is a convolutional neural network. It's used for very, very wide field of medical imaging and so on. And the idea is that it helps to combine high-level understanding the advanced range details. So it's like last predictions. Yeah, if you haven't read about UNet, I highly suggest you do. The basic idea is that it takes an input image or maybe many images, applies some convolution matches to it to the image. In this case, it learns 64, applies the convolutions, applies a different set of convolutions. Then we have the max pooling to reduce the dimensionality to the same stuff. We have like a latent space, and then we build up back to the different set of images. Okay. Then I want to say a little bit about the actual programming tools that are used to train different models. So basically, it's just TensorFlow versus Python. Both are widely used tools for deploying the machine learning models, but there's some differences. Like TensorFlow is like more graph-based, and I would say it's easier to learn, or at least the learning curve is not that steep. But it's less Pythonic, and I would say that the PyTorch, while sure it may be a little more difficult to learn, it's I feel like it's more commonly used these days and has more support. And also it has more, it's more granular and have more access to different parts. Very, I guess I said. Yeah, I would say that PyTorch should be the default choice for most modern machine learning research. And yeah, as I said, that TensorFlow is more abstract and it used to be slower, but I'm not so sure about these days. And if you want actually explicit control over the architecture and all the fine details, you definitely need to use PyTorch, I think.